Okay, so I put as title of the talk is the value of different perspectives in physics, because the models or theories that we have chosen, the focus of the workshop, you could say they are different perspectives from the usual, at least in some ways. Of course, Peter just mentioned that this Bohm-Hailey, it may not be that different from actually standard quantum mechanics. But, and again, we might find, certain important similarities with the dynamic universe and other parts of physics. But it's still, there's also a difference. And of course, the question is, well, do we need different perspectives? I'll just put this so that I have also a timing. And so, so I start something. This comes actually from the French physicist Bernard d'Espagnac, who said that Einstein thought that what is most basic in physics is not the mathematics, but rather the set of the underlying concepts. And you see, of course, not everybody would agree with this. I mean, and we have brilliant cases like with Dirac, where actually the mathematics help him to come up with his version of this relativistic quantum mechanics. But of course, then some people feel, well, maybe in contemporary physics, it's become too much mathematical. The other kind of understanding in terms of concepts is not. Actually, the sociologists of science or sociology of knowledge, they talk about arithmomania when they look at some of the physics, which is really got quite mathematical. But I mean, I don't want to take a strong stand there, but this is perhaps in the case of David Bohm, he would always emphasize that you need both mathematics and physical concepts. And Bohm felt strongly that in the way quantum mechanics were being taught, there was not that much discussion on the physical concepts. And when I talk to some of the people who study physics today, they sometimes say the same thing. If they ask a question about the physics, they are told, well, go to METSÄTALO, go here if you want to. Sometimes they say to our lesser brothers in this building, meaning philosophers might want to discuss those things. Okay. Now, and there's a quotation. This is from 1987. This was as the Bohm Fest script, so it's not surprising that he's saying nice things about Bohm. But I've always thought this interesting. And what he writes there is that it's clear that Bohm ranks first among the physicists of our generation who illustrated the deep truth of Einstein's Maxim. Many of us, including the present writer, were awakened from a kind of dogmatic slumber to take up Kant's word by reading Bohm's 52 papers. But most certainly, as Bohm's later work shows, he would more emphatically than anybody else advise us not to just jump from one dogma to another. And this is the idea. Again, you can see here is like, different perspectives. So I thought of just a little, as a little warm-up before Chris and Yvette, I thought I'll just say something about these things. Also assume perhaps not everybody knows these things from before so well. Okay, what was this alleged dogmatic slumber in quantum mechanics? And then, so what did Bohm's papers say? What was the wake-up call, so to speak? And if we take it seriously from d'Espagnac, how can we avoid jumping from one dogma to another? And finally, we could say a little bit, well, okay, it woke up people, but so what? I mean, then you fall asleep again, or, was there something substantially interesting in this different perspective that he provided? And so, okay, so the dogmatic slumber, I think, the Bohmians would say, was a state of unquestioning acceptance of the Copenhagen interpretation as the final word on quantum theory. Here, Copenhagen refers to the so-called usual interpretation. Of course, Niels Bohr, but many others, Heisenberg, Wolfgang Pauli. And so in some sense, if you study the history of physics, it's quite clear that this attitude discouraged certain lines of philosophical inquiry as meaningless. And that's very much also, from the logical positivism in philosophy. It has to do with if you can't empirically, deal with something, then you talk about it, then it's not wrong. It doesn't even mean anything. It's, the verificationist thesis. Okay, but let's quickly look at what are these so-called non-negotiable tenets, which you are not sort of supposed to discuss or even challenge. Well, were they allegedly again? Now, the one was this idea that what is primary in quantum mechanics is the so-called wave function, and also its probabilistic interpretation. So it's quite common, people say that the wave function is the complete description of a quantum system. Actually, Niels Bohr did not say that. Niels Bohr was very sophisticated philosophically, and he actually had Niels Bohr had a more instrumental attitude, saying the wave function is part of an algorithm we use to calculate observable, almost like pointer readings, like macroscopic results. But many others, people like Dirac von Neumann, had this view that no, the wave function describes reality, and it's the complete description. And so, therefore, this was kind of, if you like, part of the dogma. But it's in some sense ironic to call it the Copenhagen Dogma because it wasn't Niels Bohr, and Niels Bohr was the Copenhagen guy. But anyway, just a little bit of qualification. The other thing is that they think that the Born rule is fundamental, and this has to do, you see, people also felt that we can't really think of the wave function too much as a physical field. We think of it more as a field of probability, or there are different things like probability density. So it means that from that psi, you take the absolute value squared, that will give you a probability of finding a little thingy, a particle like your photographic plate. There's going to be a mark there. And again, you see the idea in the usual interpretation is that this probability is not due to ignorance, but actually an inherent irreducible feature of nature. So that was for many the quantum revolution. Okay. Now the other idea is there is this famous Heisenberg uncertainty idea, a principle, and idea that this is somehow fundamental limit, not just like a technical limitation, like let's apply money from the academy and we go beyond the uncertainty principle. If you do that, they probably won't give you the money unless you are really good, like Valentini or something like that. And so the idea is that it's impossible to simultaneously know certain pairs of properties like precision and momentum with arbitrary precision. The more you know about the one, the less you can know about the other. And this is a kind of feature of, you could call it complementarity. Actually, Basil Hiley would look at these things in terms of non-commutative geometry, leaving me behind. But anyway, that's the uncertainty principle. Then there's, of course, this complementary I already mentioned. And of course, this could be a bit more like, for Niels Bohr would say that these quantum objects do not possess classical properties like being a particle or being a wave intrinsically. These are more complementary, mutually exclusive descriptions. And then which one will be manifesting depends on the entire experimental context. So if you have a position measurement, in that context, you cannot manifest a momentum precisely, the two of them at the same time. And this kind of means for philosophers or ontology, it means that we can't have a single model of a quantum object that would unify the wave and the particle, which is kind of radical that in some sense, Niels Bohr used to talk about, beautiful pictures, draw about macroscopic devices, but the idea was that we don't talk about the quantum object. It's kind of almost like a Kantian. The quantum object is almost like a Ding an sich, which we just cannot model. Then there's also, I guess many of you know, in the usual interpretation, somehow this so-called classical observer and also the measurement postulate are important. So it's typical, and this is especially with John von Neumann's work, is that you think that there has to be a distinction between the quantum realm and the so-called classical realm. Actually, von Neumann felt this a bit arbitrary, that you can choose, but it's got to be there. And then, once you make this measurement with this so-called classical apparatus, there is this famous collapse of the wave function. So, and this is supposed to be a kind of discontinuous and random. Before measurement, there is typically a superposition of possibilities. You know, the particle here or there, or if the particle is has two possibilities, you hook it up to a poor cat and poison. The cat is simultaneously dead and alive before you look, right? I guess everybody has heard about the Schrödinger cat. But anyway, once there's the collapse, then it's either or. And the interesting thing here is that this collapse is an axiom. It's not derivable from the other equations. So it's something that, like, von Neumann added as an other fundamental process. Of course, Roger Penrose explores very much this kind of framework, and he has interesting ideas about this collapse. But so in that sense, Penrose is a kind of with the standard view, but then, of course, because he's a more realist in his thinking, he also differs quite strongly from the usual, just to mention that. Okay, finally, there's the idea that chance is irreducible and determinists can be rejected, which is kind of already mentioned, but it's here saying it's got a randomness. And the idea is that this indeterminism is not a temporary lack of knowledge, but a final ontological feature of the universe. So it's kind of some sort of objective chance as fundamental, which at some point people got very excited and say, oh, now we can explain free will. But then people say, well, this is a bit like dice throwing, you know. So, you know, if you're just making your most important life decision, are you going to let some sort of radioactive atom random decay decide, you know, what you're going to do, like who you're going to marry or what you're going to study? So it's not quite enough. This kind of chance is not enough for what people call free will. And then what you could say is that perhaps that's the most profound dogma. I mean, I'm putting dogma in squares, you know, that it's meaningless to speak of a particle's properties before it's measured. And some people made that into more ontological claims, saying that the particle does not have a definite position. The act of measurement creates that property. And therefore, the question, where was the electron before I measured it, is considered unanswerable and unscientific. So you could say that the usual interpretation was an anti-realist, instrumentalist framework. I mean, people have different ideas there. So if you look at, you know, Bohr, Heisenberg, you can always find a little bit of realism here and there. But still, and you see, the non-negotiable idea was that a theory like quantum theory, it should predict outcomes of measurements for observers, not to describe an objective reality that exists independently of the human mind. I mean, this is kind of philosophically interesting because it kind of does bring us into the picture. It's like something like Dr. Tarja Kallio in her PhD thesis on Niels Bohr. She really brings out that aspect. So, you know, this is kind of philosophically interesting, but then the problem was more that people were not happy discussing or criticizing this, okay? And so if somebody tried to challenge that, then they were told, well, you just don't understand quantum mechanics. Like, you know, just go do your homework. And now we come to David Bohm. This idea of David and Goliath comes from actually philosopher Mario Bunge, who said that Bohm was the David who fight the Goliath of quantum indeterminism. So anyway, now it's got a little bit of hero talk here, okay? But you see, now we already mentioned this Bohm's 52 theory, which is kind of the origin of the research program, and we're going to hear about that, like from Chris. But I just here note that it challenged these non-negotiable tenets of the usual interpretation point by point. And you see, it didn't deny the mathematical predictions. The Bohm theory actually comes from the Schrödinger equation without adding anything, right? So it had exactly the same predictions, but what it does is to provide a radically different physical picture, or we could say physical hypothesis about what's happening. And so you could add there that there's sort of, Bohm himself felt that it makes possible to also think about domains where his theory could give a different prediction from the usual. So he was already in the 52 papers, he considers that, but the theory as he presented it is empirically equivalent to the usual view. So let's just quickly have a look at this. You see, what about the first Copenhagen claim, huh? Bohm would say the wave function is not the complete description. It's kind of, if you like, it's just half the story. There is also the particle with a definite position and trajectory at all times. And then this wave function is thought to be a real physical pilot wave that guides the particle. In the Bohm's own model, it does it through so-called quantum potential. But this is anyway, this is, if you like, the naive idea. And Chris will tell us more, and also Peter tomorrow morning. What about the uncertainty principle? Well, he would say it's not a fundamental limit in the sense that for Bohm it's conceivable that one day we could actually transcend it. First of all, ontologically, his model assumes that particles do have simultaneous definite position and momentum. Maybe Peter will qualify that tomorrow morning or others, but anyway. And you see, so what about the uncertainty principle? I mean, all experiments will be the same for Bohm and the other stuff. So he would say, in the Bohm, he would say that even in the Bohm model, measurement is participatory. And what that means is that he actually used the metaphor of dance here, that before measurement, you have the object there and your apparatus there. To do the measurement, you have to bring an interaction between the two, and then you separate them. And you see, the idea is that it's a bit like a dance in the sense that the value that your pointer will have afterwards will actually be the state in which the object was after the dance, typically not before. For position, it's different. Position you could reveal. So in a way, even in the Bohm model, it's just a little bit like Copenhagen or the usual, because it's still this participation is there. And it's because of this that you see, in order to predict in the Bohm model, we should know the initial conditions at the same time. But because of this, what he would call this participatory nature, we can't do that. But it's still somehow that there's something, the uncertainty fundamentally is not in the ontology, because if Bohm thought if we could find like a subquantum level, which we would use, we might actually be able to reduce the participation. Right now we cannot. So for all practical purposes, the uncertainty principle is there, and it has been for 100 years. But it's so in a kind of. Now, what about this business of wave or particle and no visualizable reality? Well, again, as I already said, the particle is always a particle, and the wave is always a wave. There is no mysterious complementarity in that sense. And so, for example, in the double slit experiment, which Chris will be showing to us, and also tomorrow morning we'll be discussing, Bohm's hypothesis is that the particle goes through one specific slit, while the pilot wave goes through both, guiding the particle to form the interference pattern. So this is how we explain this, what seems to be very mysterious interference experiments. And you see the hypothetical process is visualizable, and Chris will prove. He actually kind of showed that beautifully already in 1979. So it's great to have Chris here, but we can see how the visualizations have developed, and also what Peter will show us. But you see, this is important because I think I think even Bohr was emphasizing that you can't do this. And so we are told that Paul Feyerabend was in Copenhagen when Niels Bohr saw the Bohm papers. And Feyerabend reports that Bohr was amazed. He didn't, in the end, warm up to it. There were some features of the theory which was not for Niels Bohr. I mean, it could be a kind of philosophical taste, maybe other issues, in physics. But definitely people were amazed because it was so much, it was kind of counter-example what people had been saying for at least 20, 30 years. 25. Okay, now about the business of determinism. The model, the Bohm 52 model, is fully deterministic. If you have the initial wave function and the position of the particle, the trajectory is predetermined. And in that sense, the randomness is not fundamental, but it's also but it does, I mean, in some ways it's for us, it arises because we don't know the initial conditions, and we cannot take a particle and put it in a certain place with a certain momentum. If we could do that, then Bohm theory would look after the rest in a deterministic way. It's again the irreducible participation prevents from us knowing the initial conditions and really measuring. But you could say that, so the Bohm theory kind of explains why you can't do that in a different way than the usual one, through these, for example, through the quantum potential. Okay, what about the collapse? Well, strictly speaking, in the Bohm theory, there is no collapse. And the wave function always evolves smoothly according to the Schrödinger equation. And you see, what we call measurement is just a physical interaction where the guided particle enters a correlated state with the apparatus. And the other empty branches of the wave function remain but do not influence the particle's trajectory. Some people worry about those empty wave packets, and then Bohm had something to say, but I won't. I talked about that in the London meeting, so I won't go into that today. But yeah, but that could be a criticism against the Bohm, or for some people at least. And then what about this meaninglessness of unobserved reality? You could say that, Bohm's theory is an apologetically realist. And of course here, because, before Bohm discovered the model, he had discussions with Einstein in Princeton. And both Einstein and Bohm felt that surely we must look for a realist theory. And so, Einstein asked, is the moon there when nobody's looking? And in this model, you can still say that even, if humanity disappears, something will be there, will be left here. Okay. But of course, even this is a big discussion. And, if you read Bohm, you see he had a lot of ideas about knowledge. And he wasn't a naive realist. And I was actually shocked when I was doing my master's in Sussex University, and I took a course in philosophy of physics. But they also made me read Karl Popper. And I thought, what a wonderful philosopher, so clear. And, and then I went to meet Bohm at Birkbeck College. And so he had all this criticism of Popper. And I was shocked. I mean, what? And at that time, I didn't even understand the criticism. I was just wondering, how could anybody disagree with Karl Popper? But, some people do. So Bohm wasn't kind of, if you like, a naive realist, but he always had that thing that he wanted to somehow give us. There was always a feeling that physics should also say something about reality as it is in itself, being qua being, like Aristotle might say. So in that sense, Bohm wanted also to do like metaphysics. Okay, so you could say things like that, just contrasting them in the Copenhagen or the usual, if you have an ontology, it's going to be quite different. And when Bohm himself was still within the usual interpretation, he actually made a beautiful theory about these potentialities as fundamental. But then when he, with the 52 model, he got into this more realist hat on, and then also this non-locality was so strongly present in the, maybe Chris and Peter will tell us about that, and others as well. which is, of course, something that Einstein didn't like, and I guess a lot of people still don't like. I think my friend physicist Klaus Montonen said that here in Helsinki, in the Kumpula, they don't like a non-local theory. But it's a big debate because other people feel strongly like Tim Maudley in that, no, we have even experiments that indicate that nature is non-local. Okay, so in a way you could say that to have this kind of alternative, you could challenge this dogmatic slumber, and if you want, you could say that Bohm forced physicists to confront the fact that their preferred interpretation was a philosophical choice, not a logical necessity or even an empirical necessity. And fair enough. I mean, you can have philosophical choices, and maybe the usual is still, in the end of the day, better than the Bohm. I mean, some people think that still, a lot of them actually. But anyway, let's have just a little bit about how could we avoid jumping from one dogma to another. And so you see what could happen, and maybe has happened a little bit with the Bohm theory, is there is actually a group that call it Bohmian mechanics, and sometimes they have this attitude that this is physics and everything else, Niels Bohr is just nonsense, and So you could have a little bit of that, and of course this wasn't sort of Bohm's idea here. I mean, surely if you read his work in the 50s, you can say that he was pushing quite hard, and maybe he had his own dogmatism, but at least later on he kind of became much more emphasizing that we could have. And this is already, I won't go through also in terms of time, I've already said all these things. This is kind of a summary of these, what was, the so-called Copenhagen Dogma. But you see, the other dogma could be then if you take the Bohm theory as the final truth. And it still has its problems which need discussions. And you could, maybe the most important is to become a Bohmian zealot, adopting the same kind of dismissive attitude towards other interpretations, like many worlds of cubism, that the Copenhagenists once held towards these theories like Bohm's theory. So this is another thing that is, and at least you could say, well, so did Bohm practice what he preached? At least when they did the book Undivided Universe with Basil Hiley, which was kind of published in '93, they have a chapter on the many worlds, which is kind of quite, does it quite nicely. But anyway, it's still, this is the big challenge in quantum mechanics, to really be able to listen to other views. And in that sense, you might just jump to another dogma here. So in a way, the idea was that Bohm himself felt that this would be more like a beginning of inquiry, and start the discussion. I'll move on with. And as you may know, that Bohm himself moved on to start discussing more fundamental theory like the implicate order, which is kind of, you can still have the pilot wave theory there, but it's not the fundamental theory. It will be more limited model. But I will move. And of course, there's this idea of dialogue that he was advocating, which we kind of describe a little bit on our workshop homepage. And just this kind of questioning. But I want to say, just to conclude, I want to say just very shortly about the value of these different perspectives. That you see, that you could claim that there is actually the theory that we could test, and so also in Portland it actually directly inspired John Bell, who started exploring the theory, and then he was interested in the question of locality, but he realized that actually, at least for him, that this non-locality is a necessary feature. And so in this theorem, he said that no theory of local hidden variables can reproduce quantum mechanics. But the Bohm theory is non-local, so it's still in the game. And so the idea was that for Bell, this was like a working model that he was using, And then finally, we could get a test. It actually did lead to an experimental work as well. Once you had this, the Bell inequalities, and this is just to conclude here, is like the Nobel Prize was actually, you could say that it was a direct culmination here, because they were testing these Bell's inequalities, and they've, you know, it's common to say that this would show that nature violates local realism, but there are other ways of looking at this. And so, so you could say that, but also you see, it's kind of, you could finally say that what you get out of there is the so-called second quantum revolution, and entanglement started becoming something, a real physical feature you could study, and of course then you could say that it's also the groundwork for quantum information science. And so in that sense, the value of a different perspective could actually even have these very concrete, at least indirect, you know, influence and inspire. And so, yes, I think this is just a summary. But so you could say that, you see, of course, it's possible that all this could have happened without Bohm. Maybe somehow it was there, you know, other people wouldn't do it another way, and why not? But you need some, at least if you have a concrete theory, then you have something to think about and develop these ideas. So who knows? I mean, this is what you could say, that it's this some sort of validation. The fact that, you know, in physics, this is kind of approaches have been appreciated is still. Well, I just leave that. This is, of course, very positive toward Bohm, and I'm sure, you know, people could have all kinds of objections and discussions, but I just set it up like that. And thank you. Thank you very much.